Okay, so good evening to one and all, and my name is George. So part of the AI Global Semi company, and as one of the verticals of the company, we have the training as well. So training not on the semiconductor part alone, but we will be going with training on the other aspects of the entire spectrum of semiconductors, as well as communication, which includes 6G, as well as AI and machine learning. So, very deeper aspects of AI and machine learning, and how that's going to be associated with the 6G and the semiconductor aspects as well. Okay, so today in this kickoff, I will be talking only about the overview of semiconductors and the general aspects of semiconductors and what is the market, and then slowly move on to what is the coverage that we are going to be doing with respect to the training that we have now. And then we will just touch upon a quick briefing about what is the physical design implementation is all about. Very quick. Okay, I'll finish off everything probably in about half hour and a half. Okay, because this is just a kickoff session. So if you have any questions, just reserve those questions because of time constraints. There are people who are joining from other places as well. I would like to have the time sensitivity on here. And if you have any questions, we'll just open up towards the end, and then we will go ahead with that. Okay. So with that, I'll start off with the session. What is the agenda? It's going to be the same. What is semiconductor? I'll start off from the basics. What is semiconductors and how semiconductor has been there, the growth story, the design future, hiring pattern, which most of you would be really keen to know about, and chip market projection, the transistor nodes, the chip development, physical design, some of the hiring companies which are hiring and which are taking people on their roles, and physical design engineers, product companies, some of the service companies, and news trends in semiconductors. Then AI perception, that's something which is new, which a lot of people keep asking me, what is this AI? Is it going to be really having an impact on the semiconductors, and what kind of an impact is going to be having on engineers like you and me, right? So, and then we'll have to have the Q&A, and then we'll move on to the step by step of the PD aspects. Okay. So with that, what is semiconductors? So almost everybody right over here who is participating is an engineer or is a techie, right? So I wanted to start from the basics. So let me start off from here. The fundamentals of transistor is like source, gate, drain, and then substrate. Okay, we call it a DGSS. Okay, so drain, gate, source, and substrate. So when I used to work on the creation of the uh, transistors, and when we do the spice analysis, we used to give these nodes, nodal points, DGSs, drain, gate, source, and substrate. Okay, so this is the symbol of an inverter. Okay, and this is an input and output. Okay, I'm starting from the fundamentals. So this is just a simple representation of a logic 0 and a logic 1. So how it works. This is the basics and the fundamentals of every semiconductors that is revolutionizing today. Today I don't have to tell. Okay, thanks to the global semiconductor ecosystem that's being developed or being in the innovation path, right? Just not in India. India, needless to say, it's taking a major big leap on semiconductor aspects, right? So then, if you look into certain aspects, you and I will be taking one or the other decisions in our everyday life with some of these gates, right? Assume these gates are there in our mind. Now, instead of that, I'm going to be having it as a semiconductor silicon, where these gates are given to me by some foundries like TSMCs, the global foundries, SMICs, and Tower Semiconductors, and power chips, and all that. Okay, so now if you look into this one, how am I going to be working on the growth story? If you look into the growth story, Initially in 1960s, it was like some kind of a single transistor, a few transistor based silicon transistor radios, then a digital clock, then a gaming console, 1 KB RAM, single CPU. Now it has gone to multi CPUs, right? Companies like Marvels and Amperes and all have gone to multi CPUs, and laptops have gone to tabs. Okay, so does it stop in the semiconductor evolution? No, it does not stop there, right? So the evolution continues to be going much deeper. Okay, if you see here, smart tablet, right? So then smart vision, right? And then smart data, smart mobility, smart payment. Can anybody tell if there is any change in this, what you're not witnessing today? You are almost witnessing everything. Okay, now smart vision, you would have probably known about the meta glasses, right? That's come, the AI glasses, smart tablet, smart data, or everything is cloud based, right? So smart mobility, smart payment, right? So now with all these, we are going full fledged, very deep, stronger in the semiconductor space, right? Now let's go into the next one. Is everything invented in semiconductors? No, much more to be done. That is why I want to take a pause and tell you that we will be needing many more semiconductor professionals in the entire globe, just not in India. India, if you see, the number of fabless design companies are increasing day by day, right? So the number of new startups that's coming in the semiconductor space, it's immense. Okay, now semiconductor chip future, right? If I see future automotive. Okay, though it has not come to India, there has been some testing that's happening with some of the companies like Mahindras and Marutis and all that. Okay, so future automotive is happening. Now, future industries, right? Then future logistics, of course, amazing logistics. Right, we see the new BYD car. So they have this future logistics where it can pop up drone from the top of the car, and then it can go to the nearby place where it can pick the consignment, come back to your car's top roof. Okay, so that is amazing. Then future production line, if you have a series of production line, how it is going to be automated. Industry 4.0 is moving towards 5.0, right? Future diagnostics, okay, now robotic surgery, everything, right? So future pico projectors. So if you look at the pico projectors, amazing. Now this is just a matter of time before you start these pico projectors in some of the markets over here, right? Future aerobics. As you keep doing the aerobics, the vital stats are taken, and then it's just going to be given to your family doctor. So future vision, right? So the same, very similar one. 2.25 centimeters in front of your eyes, you start getting your data. It is AI based, so everything. Future tablet, roll the screen into your PC and carry the PC like a pen, right? Then future transportation in Dubai, they are setting up something like transporting people from one terminal to another terminal, 4 or 5 people, very quick. Even we have multiple drone academies that's coming in. Some are really prominent, working on different aspects of drones. So there is a real great development of drones in the world. And future robotics, whether it is a quadrupod or tripod or bipod, whatever it is. So multiple companies like Gen Robotics and all are doing really great in terms of the robotics. And future mobile, take the mobile like a band onto your hand and then put it. And this is going to be again another big revolution. So now, Paul, do you and I have something in future to be worked on in the AI and in the semiconductors and in the communication space? Absolutely yes, right? So lot of work to be done in the semiconductor space. So have been listening, quite impressed with the future of semiconductors. Now, what does hiring trend look like? Okay, so now this is something which you and I will be keen in knowing what is the trend that people look at, right? So if you are 1 year or less than 1 year, yes, the hiring pattern is little less, but not as much as what it is, right? What people want you to be in an industry. 1 to 2 years, yes, they look at somebody who has completed internship, or if there are people who have done some kind of a project. But if you go to 2 to 5 years, that is where most of the people in the industry, they look at, okay, this person has done something with a design and has faced certain challenges and found out certain solutions, and with those solutions he was able to figure out certain closures. No, that is what the industry people need. So most of the people, especially with the startup boom, right, most of the people in startup, they will not have bandwidth to sit and train you. They would want to give you guidance, but you should be at least good with the fundamental concepts. I'm not telling the commands, but the fundamental concepts, whether you are quickly able to mold yourself into the ecosystem and start taking challenges and start thinking laterally to find a solution. So you fit into the 2 to 5 years band, whatever is shown here, the 2 to 5 years band. Now that is where we come into picture, where we will be giving the complete detailed aspects of the training for you to think really deep, agnostic to the tool. Let me just put it again, agnostic. You should be agnostic to the tool, which means whatever tool comes to you, it should be a matter of just about a month or something, where you should get accustomed to the tool, right? If you know what to do, there are multiple ways you will figure out how to do, right? So if you don't know what to do, then whatever tools are given to you, the tools are just a simple piece of equipment that's given, which you cannot do anything, do any solution with, right? So now 2 to 5 years is where we would be working on very deeply in bringing the expertise onto, very deep expertise onto, right? So then, now sounds promising. Can you throw some information on the semiconductor revenue market? Okay, what is happening? This might sound to be a business foil, but then that's fine, right? Because you have to know what is happening with the growth. If you see 2024, I can say even 2025, it is fine. So it's about 630 billion. Okay, so this is not from my side. I have not created this. This is from certain technical analysts, right? By 2030, look at that. It's going to be 1 trillion, right? So you see the space of logic, you see the space of memory, you see the space of green analog, and the sensors part. Logic is the biggest one, and that is where we will be focusing really deep on. Okay, so this is about the revenue projection, and let me just go on to the next one. On the region side, if you see, uh, US continues to be, North America continues to be the biggest one. Then comes Europe, and then comes Asia Pacific, excluding China. So that's a big pie, and this pie, which is the yellow pie, is now growing bigger and bigger, right? With India taking one of the biggest leads in that. Now, coming to the domain wise, high performance computing, everywhere you see it is cloud computing, AI, deep computing, everything. Then IoT is waiting to be exploded, industrial automation, automotive, consumer electronics, military aerospace, retail, and telecommunication. Small, but then it is going to have a big impact, because we are working on that very similar space in AIGC, and we are bringing in the newer technologies on the latest communication of 6G as well, and some of the projects will be associated with the designs of the 6G communication also. Okay, so then hold on, please. Let me browse on and see what are the key aspects in the huge semicon market revenue growth. Ah, got it. Okay, come on, let's see that now. if you see transistor nodes, right? So if you just follow the transistor nodes, that's coming down, right? So 1970s, 10,000 nanometer. 2021, 2022, it is about 5 nanometer, 3 nanometer. Okay, people are talking about 2 nanometer and 1 nanometer deeper. Intel has already moved on with 20 angstrom, 18 angstrom. Recently, I saw news that we are moving to 10 angstrom. Okay, does the greediness stop in reducing the technology node? No, we are trying to make the power performance area PPA, okay, much deeper and deeper, right? Power performance area. Got it? Okay, fine. So now this is about the technology node. So now some of you will be having question in your mind. What is a node, right? You're talking about 180 nanometer to 7 nanometer to 5 nanometer, 3 nanometer, 2 nanometer. What is it all about, right? So technology node is something which is the channel length, okay, that is between the source and the drain. So bigger the node, smaller the node, okay. So that will decide how much time it would actually take for the current or the electrons to flow from the source to the drain, right? So this is about one of the channels that is shrinking day by day as I am talking to you. 65 to 40 to 32 to 28 to 14, 10, 5, 3, 2, 1, 20 angstrom, 18 angstrom goes down. Okay, this is about the node as you can see the definition. Now let us go to the next one, the FET innovation, right? So earlier up to 28 nanometer, maybe some of the devices that you and I today use are planar FET, right? So that's 28 nanometer planar FET. You can see the gate that's sitting on top. Then you see something that really revolutionized the world, which is called as FinFET. I remember when it was launched, I was in one of the discussions. One of the person from Israel had actually come and given a very deep technical talk on FinFET. Now we are moving to something below 5 nanometer, which is the GAA, which is the gate all around FET. And then we are moving to something called as the MBC, molecular bridge FET, which is very similar to the GAA, but then much more powerful in terms of your performance as well. Okay, so these are type of the nodes and the FET innovation, the field effect transistor innovation that we have. Okay, so now little more deeper. Let's go step by step, little more deeper and deeper as well, right? So interesting discussion. Peep into chip design and product development cycle. Let's see what's happening. Okay, assume that you, me, and few of our friends are joined together. Okay, and we are sitting on a table, and now it's the era of startups. Okay, 3 or 4 years back, this wouldn't be the case, but then today, yes. Why did we identify some real-time problem around us? Okay, so I can think of real-time road terrain mapping. Yeah, this is happening in companies like Tesla and others, where they are trying to map the terrain and see how the terrain is, which can give the data to the vehicle that's coming behind this van. You can see this van here, right? So as we are speaking, the vehicle that's coming behind this van will immediately get an information that there is something on the terrain which is on the road. Okay, so but in India, I don't know how far it's going to be successful, but the conditions, right? But hopefully it will get better. It's getting better as we are seeing the developments. So try to take that high speed cam, try to put it into a lab and see the terrain that is there, right? And take that picture and try to do a image processing. For this, what is needed? Okay, from this picture I can say what is needed. Okay, the first thing, okay, keep aside the high speed camera and everything. A signal processing, deep signal processing, communication, very important. Why? Because this vehicle maps the terrain, puts it into the cloud, and the vehicle coming from behind should be immediately be able to see the data, right? So that means it is going to be real time. That is where we are working on the other aspect of it, which is real time communication, trying to reduce the latency from one RAM to the other RAM, right? From the transmitter RAM to the receiver RAM, right? Now coming to the semiconductor aspect of it, I develop a chip, I put it onto the board, I give it to the team, they develop the layers of software and firmware and everything. I put it onto the van, the vehicle. Okay, and my solution is ready. Fine, good. Now that is the product idea what I have in my mind. Now what is that idea? It's about some signal processing. Okay, good. I go to IEEE. I take one of the IEEE papers. Okay, I get the spec. Spec is in the form of a PDF. I take the spec, and I have a team of people who are going to be writing the RTL code for them. It can be a design, a block can go into a subsystem can go into a bigger subsystem that can go into the entire chip. You can have a ADC, you can have a DSC, you can have a PLL, you can have a IOS, interface, input and output. Okay, you can have CPUs, you can have signal processing units, you can have communication units, everything is written in multiple blocks here, right? And then I synthesize. That means the code that I am writing in Verilog or system Verilog, that has to be converted into logic gates, and that we call it as synthesis, right? So um, synthesis converts the code into gates. Now the synthesis has to be put into a real estate. Real estate is nothing but your silicon area. Now you'll have a question: why silicon areas? Silicon areas very expensive. Silicon is available everywhere. Later in the down the floor, I'm going to be having one discussion. Very quickly, I will tell you why the silicon is very expensive. Okay. Now, after finishing that, I will be going to the sign off part. Okay. Multiple sign offs are there. What is a sign off? I am signing off telling that my power is within control, my timing is within control, my area is within control, my physical aspects of the chip is within control, right? So that is what is called a sign off. An important part that we will be discussing more in detail is the static timing analysis, which will be from the synthesis through the physical design through the STA final sign off as well, right? Then my design has to be given to say TSMC in Taiwan or global foundries in the US or wherever it is, and they will create the wafer, right, and the silicon, and that silicon will be available, and I'm going to be going to be putting that silicon into the board, and my team is going to be developing the software that is needed. Okay, now this will take a good amount of time, maybe months together, maybe a couple of years in certain R&D related projects, right? So in process, when this is happening, 1 2 3 4 5 6 7 8, when it's happening, once your RTL is ready, that RTL can directly go to 9, 3 can go to 9, right? But the 9 will be an FPGA, field programmable gate array, where it can mimic the silicon, and my software team from day one, when the RTL is done, they can start developing their software. I hope everybody over here are able to understand the supply chain aspects of this 1 2 3 4 5 6 7 8 9. Now, once that is complete, the software firmware is done, right? And now, if you see here, we will be having training on the verification side, design verification, right? We'll be having on the layout side and the circuit design, and we'll be having training on the design for testability, right? And also the silicon validation, right? So these are all the other aspects of training which will go into every part of your supply chain. Now that will go into your cam, that will get into your van, and that will start communicating to your cloud, right? So now everything is good, but since we are going to be focusing deeply on the physical design aspect, I want to know more about the physical design part. So this is design partitioning, right? You can see multiple colors over here, correct? So every color is one design, right? One module, a submodule, okay, or a subsystem and all that. All these design partitioning is floor planned. Okay, all your IPs and your macros and hard macros or hard IPs are kept at different locations within your silicon area. That entire rectangle is your silicon area. Then placement of standard cells. Then you will go into the crockery synthesis, which is nothing but your circulatory system. From your heart, your blood is pumped, right? The same way the clock is pumped for every pulse. You go to a shop, you ask for your laptop. Okay, can I get a laptop which is 2.5 gigahertz? Okay, so who's liable? The clock tree synthesis expert is liable. So we will be covering detailed aspects of the clock tree synthesis, and then we will go into the routing part where all the routing happens in a orthogonal fashion, right? So we will cover every detail of it step by step, one by one. And then there are two parasites, in fact three parasites. We will be bothered about only two parasites in our chip, which is your resistance and your capacitance. Okay, so then we will be extracting that. That will tell how much time current is electrons are taking to flow through a particular metal from point A to point B, which can be say 200 microns away, right? Once that is done, then physical verification. Are two metals very close to each other? That is the question, right? If it's very close, TSMC will not agree. They will tell, I have given you the rules. Please follow the rules and make sure you are complying to the physical aspects of the verification. That is, no two metals are next to each other. I'm just giving one example. Formal verification, it is associated with the data that's coming to check the logical functionality, right? Then static timing analysis, how good is my the design in terms of my expected frequency. Power everywhere. Power, you turn left, you turn right, it is about power. Okay, IoT devices are becoming more and more power hungry nowadays, right? So that's the flow that we will be going deeper and deeper as we are getting into the design, right? So as a hiring manager, what does my company need from any candidate who's approaching me for job, right? So you should definitely be knowing fundamentals of digital design, layout, Linux OS. Yes, it's a mandate. And then the design flow, then synthesis, PD, fundamentals of DFT, then introduction to power, IR, and then placement, clock tree synthesis, extraction, sign off, and then timing closure, and then equivalence check, like different aspects of sign off, everything. Scripting is mandatory, and I will touch upon that a little later as well. And deeper aspects of timing closure, which is static timing analysis, and low technology nodes based technical aspects. Okay. Now, if you look into the value chain, because why I'm telling all this is you should know the basics. This is a kickoff session. You should know the basics in the supply chain before you even move on to the deeper semiconductor aspects as you're taking it as your career, right? So now, ARM, imagination, right? Cadence, Synopsys, and all these are design IP companies, design automation companies. We have Siemens EDA as well in electronic design automation. Equipment, if you see, there is a company called ASML, okay, on the extreme UV, right? They are one of the best in terms of developing, right? So I don't know if there is anybody else. There is a claim that there are a few more who are trying to develop extreme UV similar to ASML, but I'm not sure. But there are a few more. Then comes Lamb Research and Hitachis and ESMs and Rextons and everything, KLAs and everything. Raw material. Okay, we don't have to know about it. Okay, who has to know about them? TSMC has to know about them. Fine. Then advanced testing and packaging. Multiple companies are there globally. We have here Tata's, CG Powers, and Murgappa Groups, and etc. Right? And foundries, TSMC, Global Foundries, UMCs, SMICs, Power, Tower, everything. Fabulous design companies. You can see all these, I don't have to tell. NVIDIA, one of the greatest companies that we have seen in the recent growth, especially because of the explosion of AI, right? And then integrated device manufacturers. So these are all the device manufacturers, different companies which develop microcontrollers, starting from microcontrollers to automotive chips and everything. Value chain, right? Great. Now, if you see what are all the startup companies in what areas they work on. Today, if you ask me, GPUs, AI, NVIDIA works amazingly great, right? So now, then low power, everything is getting battery powered. And then if you see 5G, 6G, satellite communication, slowly each and everything is moving on to the satellite based communication, different protocols. are getting standardized and eventually ratified and brought into the market, right? So we come as one of the key players in developing that as well, right? So few product companies, if you know, so some of them you will be able to quickly identify. Okay, you can have a quick glance of this, right? So many more are there, right? And now, if you see, some of the service companies are here, some of them merged and they have gone. Now if you see here, these are all the AI companies which are developing silicon themselves, right? Some of them are merged under bigger companies, but some of them, okay, these foils I made a few months back. So you can see some of them uh, are working on real cutting edge silicon development. If you don't know, they have presence in India or indirect presence in India through some of their development centers here as well. Okay, so the scope is getting bigger and bigger day by day for semiconductors. Some of them may be on the medical side, some of them may be on the communication side, some of them may be on the drone side, some of them may be on the automotive side, and it keeps going, right? The list is endless. Now TSMC, UMC, Tower, IBM, IMEC, Power, Vanguard, Samsung, Intel, Global Foundries, so many, right? So Power Semiconductors is one that is working with Tata here in Gujarat. So we will be having our indigenous 28 nanometer and even lower nodes in a couple of years' time, with which the entire ecosystem is going to be completely developed within India, right? TSMC holds the biggest pie. Taiwan Semiconductor Manufacturing Corporation holds the biggest pie, close to about 58 to 60+% in terms of the global fabrication, right? And now let's see some news. I'll just have a couple of points on that. So 550 billion, Japan thinking, okay, earlier they were having flagship products in semiconductors, but they took a seat back. But now they are trying to come back against China, Taiwan, and Korea. So this is the recent news. I think this was given in September, October times, right? For 550 billion. And if you see global foundries below that, 1.1 billion expansion mainly for automotives. And this news made in America, but not by Americans. The STEM gap in the chip industry was released in June, right? So when it was released in May, June, why this news? Okay, I can see that it is May 17th or something like that, right? Why this is because most of the people who are developing silicon in the science, technology, engineering, and maths streams are predominantly from India. That means we have bigger scope. Only thing is you have to get into the right kind of a thinking with which you will be able to get in one or the other part of the supply chain of silicon development, right? Then Taiwanese chip makers, TSMC sees near 40% jump in the net profit, right? Global news, everything is positive. You can go and Google and check. Things are happening, okay? And now, if you see Nvidia 3.4 trillion, okay, and TSMC 1 trillion, Broadcom 1.1 trillion. Rest of the things comes as few billions around it, and this is poised to grow bigger and bigger, right? The market cap, right? So now VLSI in AI, Graphcore 1 billion, semiconductor market to reach 1 trillion by 2030. I already showed you. Chipping the way IT semiconductor sees companies hiring surge. Okay, but if you see some companies, why they are not hiring, that's probably because they are now churning the way designs are happening, right? Now if you ask me what is that meaning of churning, if you know the concepts, then you will be a right fit, right? If you know only certain commands and tools to blindly do based on certain directives by somebody, then you are going to be only a technical clerk. Here we are going to be imparting the training that is much deeper, where you can start thinking deeper and deeper in your own development, whether you're going to a multinational company or a services company or a startup company across any domain of automotive or drones or communication or GPUs, you will be able to think and develop certain things all by yourself, right? So that hiring is definitely getting, and this is August 25th, 2025 news, right? Now, automotive, one special aspect of automotive, this is a couple of years back, most of the automotive company are trying to develop their own silicon. Samsung is trying to develop it for Tesla. Ford and General Motors are trying to develop it with global foundries. Volkswagen are trying to develop their own chip. I never knew that. One fine morning, it was a surprise news for me. Hyundai, okay, they are connecting with some of the semiconductor giants in Korea to develop their own chip for their car. Now, car is not car, no dashboards. Dashboards or infotainment systems are now moving to computer on wheels or data on go, COW or DOG. So that is something which the world is moving towards in space in the area of automotives, right? And if you see market size 2024, and it's growing. And if you look into the second one, semiconductor production, US in the year 1990, right? 1990, they were kind of leading, but we come 2015, 2020, the market share has been taken over by Taiwan and China and Korea. But now schemes by US and Europe, they are trying to bring back that much deeper and deeper. How does India? India is also playing role. India is not there in this, but eventually the growth in India is going to become the same chart. Maybe next year, same time, if I'm talking, I will be able to give a much better, clearer picture with India also presenting its figures here and this, right? So then coming to the next one, fab jobs. I wanted to put this because there was a big requirement for fab jobs by Tatas and CG Powers and other companies which are working allied to the fabrication. Right now, they went to Taiwan. They set up a hiring unit there for a couple of days, and they tried to hire few people. And I met some of them from Philippines and others Vietnam, where they were brought to India and they have been deputed to India for a few years to work on it. Right. So my question now is, can we understand the ecosystem and develop ourselves to get into the full ecosystem, not just the design part of it, but also into the fab, which is becoming more and more prominent in India, right? So this is about the fab, and the requirement for people across clean rooms, across packaging, across testing, across validation are growing more and more every day, right? And one question, whenever I talk to people, I connect to a lot of people, and a lot of people are connecting to me to get the boot camp training done. So I'm a little concerned, will AI take the job away? I have only one statement to tell you: AI will never take your job away, but somebody who knows AI will definitely take the job away. Now, that, how to differentiate, if you see this, an IEEE paper, okay, it was published. If you see 1, 2, 3, 4, 5, 6, if I have to give indexing of this, okay, from left side, 1, 2, 3, 4, 5, 6, the fifth one, okay, the bottom row, second one, that seems to be a better floor planned chip in your silicon area. And that, if you see, that is human based. I am not telling it. You can just put the heading into the IEEE or into Google. You yourself can check it, okay, and you will be able to find. So human intervention today, because of various connects to different aspects of supply chain, from your foundry to your VLSI, to different aspects of VLSI, is not that much capable, even if some LLMs are getting developed in the AI space, right? But today, you and I are more important for the design and development, right? In various aspects. Now, some codes are available. Can AI do the code for me? They can. I can give a real example. The recent times I was working with one of the designs. So I took a code from AI, but the verification and simulation team came back and told, so this is absolutely not working. This is just giving me so many errors. Now, where do we go? Should we go with the errors, list of errors, to your X or Y or Z AI tool to tell it to fix it for me? They won't fix it. And the time I'm going to ask them to fix it for me, I myself can do it. Right? So human intervention cannot be removed from the AI's perspective today. Okay, maybe 15 or 20 years down the line, it can maybe the LLMs can grow to a level where it can kind of replace to some extent, but not today. So your need and my need are absolutely important. Okay, so AI cannot take, that's the final word we can say. Now, this is done. The first part is done. What I'm going to do is I'm going to take one of my favorite topics, which is the little more deeper aspects of what we are going to be working on, little deeper into the physical design. We all know smartwatch. I wanted to take a mobile phone, break it up and see, but then smartwatch seems to be much better action because everything is happening through a smartwatch nowadays, right? So now let me go through the tear down of it. I have a watch. Take the watch, cut it open. At the back, I can see the circuit board, right, with all other things on my PCB, in my motherboard and daughter board, right? So let me take the bigger aspects of my board. Take this SOC as you can see here, okay? And now, if you see the SOC and top view and the bottom view, this is a chip's bottom view. This is a chip's top view. You can see all those bumps here. Okay, you can mount it onto the board using something called as different kinds of mounting are there. The most prominent one is SMT, which is surface mount technology. That's on the packaging. Say we will leave it to the packaging experts through the globe, right? So about 8 million, 10 million, 12 million, millions and billions of transistors that's getting, okay, added day by day as we speak, right? So now can we see how the implementation of a SoC works, right? I have the spec, I download the spec, right? I keep the spec with me and I start developing my code. I can get the help of AI here and there to write my code a little bit here and there, but I am responsible for connecting it, right? So ready to write the RTL code in Verilog, fine. So step one done. Maybe this will take a couple of weeks time for me to get that thumbs up. Step one is done. RTL code. This is just a representative diagram of my FSM, right? And then I have my team who is going to be writing the RTL code for me. This is a representative diagram of the RTL code, either in V or in .sv, Verilog or system Verilog. Verilog stands for verifying logic. System Verilog stands for system verifying logic. Verilog, why we call it as verifying logic is because Verilog was initially brought into the market mainly for verification purpose. Later, it was converted into a real time. Now, VHDL, very few people use. Some people use in Europe, but not much, right? It's mainly moving to Verilog and system Verilog. So I have my FSM state machines, right? And we'll be going deeper into state machines later as we go on. So RTL is written in VHDL. Step two, RTL coding is done. Easy said, but then it would have taken probably about a couple of months more for me. Right now, ready for design verification. Am I clear with what I am doing? Do I need a verification team to verify my code? Yes, they will have to look into my spec. They will have to write a verification environment. They will have to take my design as DUT, design under test, and they will have to tell, verification team has to tell that the RTL code that I am writing is good to go. If it is not good to go, then it will not produce the chip as I expect. This is my functional intent, right? Fine. Now with design verification is done, the next step is also done, right? That would have taken probably another couple of months, totally about 5 months done. Okay, verification test bench. I give the stimulus. My design RTL code is there in the purple color in between. I will check the results, right? So to err is designer, to fix is or to verify is the DB engineer, right? So they will tell what is the error, where is the error. Ready for synthesis, step 3 done. Okay, maybe 5 to 6 months done from the initial. I have my RTL code. I take the RTL code. As you all know, I put it into elaborate stage. Simple K-map optimization. There are different algorithms, Shannon cofactoring, then McKinsey, and then DAG, directed acyclic graphs. Okay, and different automate algorithms work on converting the code into the second stage, which is Boolean equation, into my gates, which is called as netlist. As you can see here, it will be seen as netlist right here. Now, the RTL code was my functional intent. I wanted USB. I wanted a camera DSP. I wanted a communication 6G chip. That is my functional intent. How fast it should run, that is my timing intent. That timing intent has to be given through some form to give functional intent is RTL code, very long. But the way to give or the form to give the constraint or the timing intent is called as SDC, synthesis design constraint. Okay, you see as the second one. And the other raw material that will go into my synthesis, that is called as libraries, right? So these libraries are given to you by TSMCs and global foundries and SMICs and others. They give everything. Synthesis tool will optimize and give you netlist. And that netlist, we are now ready for PNR. Step 4, thumbs up, right? Maybe you had a couple of months, 7 months over, right? Why do you call it as a netlist? Because every connection from a NAND gate to a XOR gate to a NOT gate, the interconnect is connected through certain copper or aluminum wires, predominantly copper, right? So that is called as a net, interconnect, net. And list of net connecting logic is called as net list, right? So that is the definition of net list. Now, reading the netlist, everything is good, constraints available, lib available, and v available. So all my intents are there. One more intent I had, let me think. What is that intent? Power. Yes, I had a power intent. My design should work within X milliwatt. If my design has to work within X milliwatt, 40, 50, 60 milliwatt, then I have to tell the tool from beginning that this is my intent to make the chip work in that particular power. Now, is that a work of a physical design engineer? Absolutely. Along with the timing intent, along with the functional intent, along with the synthesis physical design STA, I have to develop. That also we will be going very deep, which the industry needs today, right? That is called CPF or UPF. UPF is again a standard, right? Unified power format, just like your SDC. So we will be covering every details of the power intent through your UPF file, right? Now everything is done. Now files are there, but stop. Is everything of good quality? You know software. Garbage in, garbage out, right? So I need to check all of this. So if I need to check all of this, I have to do something called as check the design, check the timing, and check the library. I have to do the check and I have to find out if there are any issues inside. It will flag out, and we will be looking at certain aspects of checking and flagging the errors. You should keep your hands onto the log files. You should check what are all the problems, fix it. That is where human intervention comes into picture. If I take this and give to some AI tool is just going to sit there and tell, I don't know what to do, right? Now, this is called as sanity check, and sanity check is nothing but sanity, purity, quality. Okay, they will check the quality of each and every file that I have given: Verilog file, SDC file, and Liberty file. .v.sdc.lib, right? Now, step 5 is done, sanity check is done, ready for flow plan. Now, let's call the architect, right? So, I have a particular silicon area available for me. With that particular silicon area, where to place, what to place, how to place Should I orient it 90 degrees, 180 degrees, 270 degrees, 360 degrees? How are the connections from my input port of the chip to internal logic that is inside? That is responsibility of you and me. We have to do it, right? Now, once that is done, so as you can see, this is again a openly available diagram. I just put it for representation purpose. All the logic is sitting here, right? All the macros are sitting here inside. All the logic is sitting outside here, right? So now that is complete and everything is finished, and I am ready after my floor plan and macro placement. My step 6 is complete, and now it is time to bring in the electrician within you, which is, if you turn around and see your connections in your house, you have phase and neutral. Very simple. Here at the micro level, you will have to do the same phase and neutral, but here it is called as VDD and VSS. But easy said, it's not a physical wiring, what you pull and do. You have to do multiple calculations to put your connections. So how much of current density should pass through? What should be the current that should come to your logic? What should be the current that should touch your macros, right? What should touch your IPs, logic? So that is dependent on the connection, the power planning that you work on. So power planning is the next step, right? So what did I do? I had the code, I verified, I took the spec, I wrote the RTL code, I asked my verification team to verify it. Then I went to my synthesis team to synthesize it. I got my synthesis netlist. I did my sanity check. Then I did my floor planning and placement. And now I am coming to my power plan. Okay. Now power plan is done. Entire PG, which is called as power grid, is completed. And now I will be completing my step 7. You can add maybe another 2 months, maybe a year plus 1.1 years. Okay, from ground zero, your design life cycle. Now, this entire chip, you can see inside that all the logic is sitting inside. Placement algorithm will come. It will go and place the standard cells. I've been telling the word standard cells, standard cells, standard cells, right? So now, what is the meaning of standard here? The meaning of standard is nothing but height of the cell is same, width of the cell changes. Now you go back to the previous foil that I was talking about, right? The channel width and the channel length. Okay, that is one of the key factors in the height of the standard, in the width of the standard cell. Height of the standard cell remain static for a particular library, right? So you see here, the between VDD and VSS, the height remains same. Okay, now these standard cells are all placed very close to each other. Boom, there is a lot of congestion. It can be power related congestion, IR based red hotspots. It can be too many cells placed very close to each other that you won't be able to do the interconnect. Okay, then you will have to move the cells little apart. You see the red color hotspots, you see brown color, you see yellow color. These have to be changed. Right now you'll have to use algorithms which will be working on doing this. So a lot of analytics goes into this, and that we will be covering in detail, which the industry needs, right? So setup timing. So if you know, if you have done something in your BTech or MTech, you will be knowing something called as a setup or a hold timing. So predominantly setup timing should be checked here. Along with the certain other timings are to be checked, but setup is the most common one that you need to check. And power also within my limit. So many, maybe 40 microwatt. Finished? Right. So placement is done. Step 8 is done. We are going to the closure. Now coming to the development of the circulatory system of my chip. Okay. If you know, this is one of the key aspects of your entire design cycle, right? If you know how to create the circulatory system of your chip, that is clock tree synthesis, you see CLK as your blue port, right? This CLK, if you see Next to CLK, there is a F of 1. And far away on the right side, you see a F of 4, right? The CLK, the length goes equidistant to the closest F of 1 and the farthest F of 4. That means it's equidistant. That means, can you see a letter H here? This is what is called as H tree. Now, we have other aspects like multi-point CTS, multi-source CTS, different kind of CTS, but the common one is the spine tree and H tree based synthesis. So you'll have to write the spec for creating this, and this is what the companies will be looking at in developing the spec for themselves. They will look at what you are capable of, and we will help you in developing that as well, right? So now skew, if you see what is skew between F of 2 and F of 3, if the arrival of the clock changes, then it is called as skew. Between F of 2, if F of 2 gets it at 500, F of 3 gets it as 510, then 500 and to 510, the clock, one edge of the clock, then the 10 picoseconds is called as skew. How to reduce it, how to increase it, why should you reduce it, why should you increase it, depends on engineers like you and me, and we will be covering detailed aspects of that, right? So now step 9 is complete, clock tree synthesis is done. I'm going to the routing part. Okay, now routing, if I see, my routing will be looking like this, representative diagram again, right? So everything is substrate, field oxide, substrate, metal 1, substrate, metal 2 perpendicular to metal 1, again substrate, metal 3 perpendicular to metal 2, substrate, metal 4 perpendicular to metal 3, like that it keeps going. Okay, metal 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, like that, till your top level metal or your RDL, which is a redistribution layer, which can go diagonal. Oh, diagonal. Do we have diagonal routing? That is pseudo diagonal, which is your diagonal is actually small blocks of rectilinear connections, small staggered boxes. Okay, so that is what is about routing, and we will go deeper into the routing aspects as well. Right, once the routing is complete, maybe about 1 year, 2 to 3 months has gone by. Now, parasitic extraction, I told you R and C. We all know R is equal to rho L by A, C equal to epsilon A by D. Just multiply them, it will give you the time taken for the electron to pass from the metal point A to metal point B. That's all. Very simple. Resistance into capacitance. If you don't have resistance, don't have capacitance, it will just flow in no time. It will just reach the other end. So this delay is important. So we have two delays, right? If you have an AND gate that is connected through a metal connection to a OR gate, the AND and OR, right? So if the AND gate has a delay, if the OR gate has a delay, right? This AND delay and the AND delay and the interconnect delay put together will be the total delay. Anyway, we will get into the detailed aspects of those as we get into the complete design. Okay, so you will not get into one simple net and keep checking all that. This will be an algorithm that will run through a tool, and that tool is going to extract the RNC for you and give the RNC for you. That RNC you will be taking and you will be continuing with your physical design. Okay, that is called SPEF file, standard parasitic extraction format. This gives the resistance and capacitance for the interconnect wire. Okay, good enough. Ready for static timing analysis. Step 11 is complete. How much time is gone? Maybe I can attribute a couple of weeks for that, or maybe a month for this. Worst case, then sign off. There are multiple sign offs: timing sign off, power sign off, physical verification sign off, formal verification sign off, etc. etc. Some of them which you will be going through in detail are, say, in your STA, what is the period, uncertainty, timing window, noise, process, voltage, temperature, setup, hold, disable timing, latency, general clock. So many things as I have given in small writings around that particular waveform, right? And also the particular circuit, right? So everything is done, completed, tick, 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 everything is a tick, great, thumbs up, good. And I expected my chip to work at say 1.7 gigahertz, and my chip works at 1.7 gigahertz, 100% for sure, within the power expectation and within the other side of expectations. Good. GDS2, graphical data system stream, GDSS, or in short, we can call it as GDS2, right? That will be given to TSMC Foundry. They will give the silicon pack to us. Now, in the training, you will just give the GDS. We are also trying to see if we can connect to some of the foundries where they can give a silicon as a representative silicon, or uh, a simple design, which is a training based silicon, which may not contain, but it incurs cost. But I don't know if that's successful. But till this point, you will be working on the design aspect, and you will write out a GDS, and with all the conditions and checks and the validations and analysis, everything done, right? So, and you will also have an option to put it into the FPGA and see how your design is working. Okay, so step 12, STA is done. Then I wanted to give you the other aspects, what's happening on the other side of the country, which is Taiwan or Korea or US. It goes into the fab. Fab makes this wafer. Wafer will have your chip ready, and the chip will be put into a package, and package will come as a working silicon to you, and the working silicon will be your SoC that is actually going into your smartwatch, what we tore open. I hope I gave a very clear supply chain connect of the aspects of the development. You fit into one part, or you cannot be into everything, because we are all human beings. Even I am not into everything, I am only into one part of it, right? So there are people who are working in different parts of it, right? So they will take care of their, but I will cover each and every aspect. So when I am doing the training, as I am doing the training, I will bring in more and more aspects of how it is connected globally with different supply chain things. This, if you do, the other person in the fab house will be able to get this better. If you do this, the packaging guys are going to be packaging your silicon better. If you do this, your automotive chip is going to be working really better for a longer time, covering various aspects of temperatures and powers and variations and spikes and all that, and it should continue to work for years together without breaking the silicon. So all that, as I am doing every in each and every stage in the training, I will be touching upon those aspects. So I will inculcate that into the impart that into the different stages of the training, right? And you will appreciate that when you're doing your hands-on as well. Right. Now, PSOC is ready to be placed on board for firmware device drivers development by my colleagues who are sitting on the software side next to me here. Right. Now, if you see, some people will be wondering, silicon is available every year, but then why is it so expensive? Why is the entire process of silicon expensive? And why are silicon people paid really high? Okay, and why is it that it's the world is fighting, starting from US to the president of the US to China to Korea, Taiwan, Japan, everybody are bringing different. I was surprised to see Oman has got their own semiconductor development consortium created. It was like some 8 months back, right? And that is one of the biggest surprises that I have. So everybody are getting into this, right? So now you can see the importance of this in the near future, right? As you people graduate to 2026, 2027, 2028, 2029, 30, the importance for people like you, right, will be immense, right? Not like a software person who just develops, because software, any mundane, any repetitive, kind of work is getting replaced by automation. When I say automation, AI, right? So that's what I meant. So if you see silicon nuggets, that goes into purifier, and there is a process called as Zokralski, right? That will be pulling the ingot. Okay, this, you see this ingot here, it will take few centimeters to come out in couple of weeks time. You slice it, you make wafers. That wafers is polished, and now it is oxidized, right, by imparting certain oxidation techniques. And now come down your RTL design, you and I are sitting, and what the flow that we saw now, we will be developing and completing my layout and GDS, that I will be giving to the foundry to develop their mask. What you're writing as Verilog code is nothing but going to develop a mask. That mask is going to be sitting onto the wafer, onto the slice of the wafer, and that is going to develop your silicon eventually. And that silicon is going to come out as your SOC packaged and in your black casing that you see when you open your smartwatch or your mobile phone or your laptop, right? So this is why it is expensive in spite of silicon being abundant, right? Now, the prerequisites for anybody: operating system Linux, mandatory. Scripting languages, few of them are there. Okay, mandatory, you have to know TCL, right? So we are also planning to have a TCL scripting, which will be covering in detail TCL. You will be given aspects to develop your own tickle scripts. Handhold, you do it, burn your fingers, ask questions, again do it. Like that, if you do and put it in your resume, okay, that is going to convert your employability quotient much higher, right? So TCL is mandatory, Perl is optional, Python is optional. Okay, now coming, there are multiple tools that are available. So we will be using industry tools for the training here. Now synopsis, DCIC Fusion Compiler, Prime Time, Star RC, IC Validator, Formality. So different types of tools. Cadence, GNS, Innovus, Tempest, Qantas, PVS, LEC, blah, blah, blah. So many are there, right? So metagraphics. So there are different tools, OSS, Appraiser, and different tools are there. It's getting changed, names are getting changed. But these are all the fundamental tool names that I have wanted to quickly put to you. Don't bother about the tools. Tools are just hand holding things. Again, I'm making the statement. If you know what to do, there are ways how to do. If you don't know what to do, then even if there are ways how to do, you will be clueless. So long-term employability and long-term semiconductor stalwart in the industry, maybe like 5, 6, 7, 8, 10, 20, 30, 40, 50 years, whatever it is. Maybe I'm not alive as well, right? That time, during those times. But if you want to carry the lineage, you should know what to do. We will be covering aspects of what to do and how to do with the tools as well. Okay. Now, uh, let me just go on. Before I wrap up, couple of slides more. You should know some important aspects. Node I touched upon earlier. If you see 1994, bigger nodes, right? 350, 250, blah blah blah. It keeps coming. And 2025, 2 nanometer. 2028, 1 nanometer. 2031, it keeps going to 18, 20 angstrom, deeper, deeper. We are greedy. We never stop. Technology, we never stop being greedy, right? So you yourself can innovatively develop many things after knowing what to do. Okay, and then you will have ways how to do. Okay. Now, second thing, if you see the wafer, right, there is a notch at the back, and you see this wafer is not exactly round. There's a cut at the bottom. So that will tell you the Miller index orientation of the molecules within the silicon. To make it mono-oriented, the Sokralski process I told you, silicon is molten at 3,500 degrees centigrade, pulled out a few centimeters in couple of weeks time. So that process will make this. So that orientation representation is your line that you had shown there. That is shown there. Now your wafer 1970 50 mm, but you see here it goes all the way 2000 and 2000, beyond 2000. it keeps going to 300, 450, and people are working on making bigger and bigger wafers. The size keeps increasing. Okay. Now voltage, if you see, how many of you have thought about what is the voltage at which my transistor works in my mobile phone or laptop? Okay, approximately in the range of about 1 to 1.1 volt, even much lesser than that. I'm taking the upper cap. Right now, as an electrician, you are expected to make sure that you get 1.1 or 1 or zero point 0.9 or zero point 0.8 volt. Right, if you're not giving it to your logic gate, your logic gate will not behave in a way it is expected to behave. Your and, or, nor, not, XOR, everything, or it will not give you the data from A input of a AND gate to the Y output of AND gate in an expected time. Now, what is that expected time? What is the input and output that we need to see? All that will be discussed in real depth and details, right? When we get into the training, right? 28 nanometer, 5 nanometer, it has fallen down all the way, say, zero point 0.7 and zero point 0.6 volts. Transistor count, okay, do I have to really tell about it? You yourself can imagine it has gone to 10 power 10, 1 power 10. So 10 power 10 to the power of 10. Okay, that is to say, and it is increasing more and more. Okay, this is only till 2010 that I have. Okay, it is again increasing more and more. Now, one thing that I would want to tell here, there is something called as chiplet architecture. Okay, what is a eaglet? Okay, eaglet is nothing but a small eagle, right? So chiplet is nothing but a full chip where small chips are developed. Okay, and then they are put into a substrate, right? So I bring one IP, make it into a silicon. I bring another IP, make it into another silicon. Bring third IP, make it into another silicon. Put everything into a substrate. I package it and make it into a chip. The one inside silicon one, silicon two, silicon three are all chiplets. So there are different ways to connect them in the 2D and 3D. I will just give briefings about it, but I will not go into details of the architectures of that. There are standards which are there which connects various internal silicons, internal chiplets at the full chip level, and why it is used, what is the use case in the world, why are we not going for monolithic, why are we going for polylithic. Those aspects I will touch upon more and more, because those are all futuristic. Okay, next 3 4 5 years, those are all important. So that I will touch upon as I am going into deeper into the training, right? So now, battery. I want battery to be working for 2 to 3 to 4 5 days, but I'm charging every day. So what should I do? Dynamic power. I play games. Then my dynamic power will be consumed high. Leakage power. Assume you charge your mobile phone 100%. Okay, switch off your mobile phone. Keep it in your shelf. 1 week later, come and take it. Turn it on. Can anyone expect it to be at 100? No, it would have gone to 95. Why? Where the 5% went? Leakage. How to take care of the leakage? There are ways to take care of the leakage. That again, we will be working on very deeper, right? Low power. If you put the word low power in your CV resume, right, that has much higher weightage for the hiring managers, right? So this is about the two important power aspects here. But you see a dip here, 32 nanometer, 45, 32 nanometer, the power was going higher and higher. Then it dipped. Now you think back. Remember, we moved from planar FET to FinFET. The change from planar FET to FinFET made a big impact in reducing the leakage power. Right? Now, where is the leakage power for my AND gate, OR gate, NOT gate? That is there in the Liberty file that is given. Okay, and we will analyze them much deeper when we are taking the training as we are going forward. Right? So, cores. Now you see, do I need a single core CPU, multi core, dual core, quad core, oct core? Okay, so everybody prefers higher core. You can distribute your laptop's work into different cores, multi core, right? So cores are increasing. This is like I'm given a task of work to do. If I do it myself, I'll be exhausted. All my power will go off from my body. So I will collect, I will arrange three or four more friends of mine, make them also work along with me so that my power is not drained. They can also work in parallel. It will get done quickly, the work. That is what multi-core and quad-core and octa-core kind of designs work on, right? So this is about the uh, entire aspects of the kickoff. So if you have any questions, please let me know.